In this video, we'll go through question 13 from the 2017 HSC Mathematics Extension 1 exam. Part A. A particle is moving along the x-axis in simple harmonic motion, centered at the origin. When x equals 2, the velocity of the particle is 4. When x equals 5, the velocity of the particle is 3. Find the period of motion. Okay, so the first thing we should do is we should write down any information that we're given in the question. So we know that when x is equal to 2, the velocity is going to be equal to 4. And we also know that when x is equal to 5, the velocity is going to be equal to 3. So we have some relationship between x and v, between the displacement and the velocity. So can we think of any formulas which are relating to simple harmonic motion that link the displacement and the velocity together? And the one that should come to mind is v squared equals n squared into a squared minus x squared. So we're going to use this and these two bits of information. But let's just keep in mind what we're trying to find. We're trying to find the period of motion. And the period is given by 2 pi on n. So really what I'm trying to do from this is I'm trying to work out what n is so I can substitute it into that formula. Okay, so anyway, let's go ahead and sub these bits of this data that's given in the question. Let's sub it into our formula here. So when x is equal to 2 and v is equal to 4, we have the following. 16, which is 4 squared, equals n squared into a squared minus x squared, 2 squared, which is 4. And what I'm going to do is I'm actually going to expand this out. So n squared a squared minus 4n squared. You'll see why I do that in a minute. And the other one, so x equals 5, v equals 3. Substitute that in, what do we get? 3 squared, which is 9, equals n squared into a squared minus x squared, which is 25. Okay, again, I'm going to expand out. I get n squared, a squared minus n squared 25, or 25 times n squared. Okay, that's equation 2. Now, like we said, we want to try to work out what the variable n is equal to. And I can see that I have an n squared a squared in the first equation and an n squared a squared in the second equation. So we should just subtract these two equations to eliminate the a squared, or the a variable, to get rid of n squared a squared. So if I do equation 1 minus equation 2, I have 16 minus 9, which is 7, is equal to negative 4n squared minus negative 25n squared. So that's going to be minus 4 plus 25, which is going to be 21n squared. Okay, and if I divide by 21, I get 7 divided 21 is a third, or is a third n squared, and so therefore n is equal to 1 divided by root 3. Okay, and we only take the positive because n is positive, so let's just write that. N is greater than 0. Alright, so therefore our period is going to be given by 2 pi divided by n, which is 2 pi divided by 1 on root 3, which is 2 root 3 pi. Okay, and that's our period, and that's the end of that question. Part B. Let n be a positive even integer. The first part, show that 1 plus x to the n plus 1 minus x to the n is equal to that expression. Okay, so here we have one binomial, which is 1 plus x to the n, plus another binomial, which is 1 minus x to the n. And these two are very similar. All right, and we want to add these up. So firstly, let's work out or write down what they are individually, what each one is. So the first one, 1 plus x to the n. Well, this is, actually both of these are very standard for us. Right, if we know the binomial formula, we just write it out. This is n choose 0 plus n choose 1 x to the power 1 plus n choose 2x squared. I'm going to write out a few terms. Plus n choose 3x cubed. N choose 4x to the 4. That should be enough. And then let's write the final term. N choose n x to the n. Okay, let's call this equation 1. That's our first one. And for 1 minus x to the n, it's going to be the same thing, except for every second term where all the powers of x are odd, we're just going to have a minus. So this is going to be n choose 0 minus n choose 1 to the power x plus n choose 2 x squared minus n choose 3 x cubed plus n choose 4 x to the 4. The next one would be a minus, and then we continue all the way up to n choose n x to the n. However, we don't know whether this is going to be positive or negative. So it's going to be negative 1 to the power n. Okay, we actually do know, but I'm just going to write this just for the moment. Okay, because we know that n is even. Okay, since n is even, this is going to be negative 1 to the power of an even number, which is going to be positive 1. But it's fine to just leave it like this for the moment. Anyway, we want to add these two up in order to get the left-hand side of what we're required to get. So if we get 1 plus 2, equation 1 plus equation 2, we have 1 plus x to the n plus 1 minus x to the n. Okay, this is going to be equal to n choose 0 plus n choose 0 is 2n choose 0. And then n choose 1x minus n choose 1x will cancel each other out. I'm going to have the next term, 2 times n choose 2 x squared. And then again, the x cubed terms will cancel out. And in fact, every second term, all the odd powers will cancel each other out until we get up to 2 times n choose 4 x to the 4, all the way up to n choose n x to the n plus negative 1 to the n choose n x to the n. Okay, now I know I'm being very pedantic here, but I want to show the marker that I know why they've told us that n has to be even. Okay, so that means I'm going to have 2 n choose 0 plus 2 n choose 2x squared. I can put dots in from now. And then I can say 2 times n choose n x to the n. And here I'm going to say since n is even. So now the marker knows that I know what I'm doing, and I haven't accidentally made a mistake, which has turned out to be a correct answer. Okay, and then I can factor out a 2, and I get exactly what I'm required to prove. N choose 0, n choose 2x squared, n choose n x to the n. Okay, and we've proven, so you can write QED. All right, now part 2. Hence show that this expression holds. I'm not going to read that out. Okay, so let's have a look at what we have. We can see now that we've started to get an n coming out. If we're just looking at the left-hand side, we can see that there's a reduction in the power and an n has come out as a coefficient. That almost always indicates that we have to differentiate. Okay, and you can clearly see that if you differentiate the left-hand side of the result that we just worked out in the first part, you're going to get the left-hand side of what we want to prove in the second part. Okay, so maybe let's go up and let's call this in blue star here. Okay, let's write this left-hand side really quickly. So we want to differentiate. I'm going to star it again in blue just so we know what we're talking about. We want to differentiate that star with respect to x. Okay, so if we do that, we're going to get n times 1 plus x to the n minus 1 plus n times 1 minus x to the n minus 1, but we also have to multiply by the inside derivative, which is negative 1. Okay, that's where we get that minus in what we want to prove. In the left-hand side, that's where the minus comes from. And then when we differentiate the right-hand side of the blue star, we get 2 times. All right, now n choose 0 is actually just a constant. So when I differentiate that with respect to x, it completely disappears. So that term becomes 0. Then I'm differentiating with respect to x. So I bring down the power, n choose 2 is just the coefficient, and I reduce the power by 1. The next term would have been, n choose 4x to the 4. So when I differentiate that, bring down the power, n choose 4, and I reduce the power by 1, etc. all the way to the end, and I'll get n times n choose n x to the n minus 1. Okay, and then the only thing we really need to do now is to factor out the n here and bring that multiplying minus 1 in the middle. So that's n times 1 plus x to the n minus 1. This is a minus 1 minus x to the n minus 1 equals what we have on the left-hand side. N choose 2x, 4, n choose 4x cubed, dot dot dot, n times n choose n, x to the n minus 1. Okay, and that's only worth 1 mark, so it's not going to be too difficult. Okay, and that's also QED. We've proven what we want to show there. How about the last part? Hence show that n choose 2 plus 2 times n choose 4 plus 3 times n choose 6 all the way up to n over 2 times n choose n is equal to n times 2 to the power n minus 3. Okay, so here I've just written down the result that we had in the previous part. And the question does say hence, so that means we're going to be using the one in the previous part in order to help us with this part now. So when I look at what I want to prove, let's have a look at the left-hand side. I can see that there are some similarities between this and what we had previously. I can see that I have this n choose 2 here and an n choose 2 here. I have the n choose 4, n choose 4, n choose 6, there would be an n choose 6 sitting here. And then I have the n choose n and the n choose n. And if I look very carefully, I can also see that the coefficient of the n choose whatever in the left-hand side of what I want to prove is exactly half of the coefficient of the same thing inside the brackets on the right-hand side of the last part's result. So what do I mean by that? Well, here I have a coefficient of 1, which is exactly half of 2. Here my coefficient is 2, which is exactly half of this 4. My coefficient is 3, and the coefficient here would be 6, which is exactly twice 3. And I can see that this n is exactly twice this n on 2. Okay, so what I want is already half of what I have. Okay, and the final thing that I can see is that I don't have any x's in what I'm required to prove. So all these x's that were in my previous part's result, they've all seemed to disappear somehow. Okay, so that's the final thing we need to keep in mind. So how can we get rid of x's? Well, if we sub x equal to 1 in, that doesn't get rid of the whole thing, but the x disappears. Okay, so we wouldn't want to sub in x equals 0 because then each term would just become 0. So, but if we sub in x equals 1, we're left with the coefficient of x, but the x disappears. So let's call this double star, and I'll label it in green. So sub x equals 1 into double star. And let's have a look at what we get. Okay, so on the left-hand side, I have n times, in the brackets, the first one, I'll have 1 plus 1 to the power n minus 1, so that's 2 to the n minus 1. And the left-hand, not the left-hand side, I'll have minus 1 minus 1, which is 0 to the n minus 1, so that's just going to be 0. Okay, subbing in on the right-hand side, I have 2 times 2 n choose 2 times 1 plus 4 n choose 4 times 1 cubed, which is just 1, all the way up to n choose n x. Oh, I don't need that x. Let's get rid of all that. That's n choose n x, or 1 to the n minus 1, which is just going to be 1. Okay, and I can see I can factor out an n on the right, not an n, a 2 on the right-hand side here. So if I factor out another 2, I'll have 2 times 2, which is 4 on the outside. N choose 2 plus 2 n choose 4 plus the next one would be 6, and then I take out a factor of 2, which gives 3 n choose 6, etc. n on 2 times n choose n. Okay, and I can see that this is exactly what I want to prove on the left-hand side. Okay, so I can divide by this 4, and I have n 2 to the n minus 1 divided by 4, but what is 4? 4 is nothing but 2 squared, so I can write it as 2 squared, is equal to n choose 2 plus 2 times n choose 4 plus 3 times n choose 6, and so on, n on 2 times n choose n. Okay, and then I can just use some indice rules, and I have n times 2 to the n minus 3 equals n choose 2 plus 2 times n choose 4 plus 3 times n choose 6, all the way up to and including n on 2 times n choose n. Okay, and that's exactly what we want to prove. So that's QED, and that is the end of question B. Part C. A golfer hits a golf ball with initial speed v meters per second at an angle theta to the horizontal. The golf ball is hit from one side of a lake and must have a horizontal range of 100 meters or more to avoid landing in the lake. And here we're given a small diagram. Neglecting the effects of air resistance, the equations describing the motion of the ball are x equals vt cos theta and y equals vt sine theta minus a half gt squared. Where t is the time in seconds after the ball is hit, g is the acceleration due to gravity in meters per second squared. Meters per second squared. Should get that right. Do not prove these equations. Alright, so we're given the equations. First part says, show that the horizontal range of the golf ball is v squared sine 2 theta on g. Okay, so we want to find the horizontal range of this ball. Now, let's write down what we're given. We're given x equals vt cos theta and y equals vt sine theta minus a half gt squared. Now the horizontal range means I want to find how far in the x direction I've traveled. But what information do we have in order to sub in for x? We don't really have anything at all. So we have to think, what is actually happening when the ball has landed? Well, we know that the y value of the position has to be equal to 0. So when the ball has landed, it's a golf ball, so when the ball has landed, we have that y has to be equal to 0. So that means if we sub y equal to 0 into our second equation, we get 0 equals vt sine theta minus a half gt squared. So from this, I'm able to work out the time at which the ball has landed. Now this is a quadratic equation, which is good. I should expect 2 answers, and I already know what one of the answers is. If I have a very quick diagram here and I have a look, this is the path of my ball. Now obviously at t equals 0 we have y equals 0, but we also have y equals 0 at some other unknown time, which is what we're about to work out. Okay, so if I solve this for t, I can actually factor out a t here. I get v sine theta minus a half gt. Okay, that's equal to 0. So I have 2 solutions. I have t equals 0, and the second one would be, let's see, 2v sine theta on g. Okay, that's just solving that quadratic. So when t equals 2v sine theta on g, I'm actually at this point right here. Okay, so I can substitute that into my equation for x, which will give me the distance that I've traveled in the horizontal direction. So when t is equal to 2v sine theta on g, my pen's playing up, we get x equals v times 2v sine theta on g, so that's my value for t, times cos theta. Okay, so I have a v times a v, which is v squared, and then I have 2 times sine times cos, which is exactly sine 2 theta. That's the double angle result for sine 2 theta. Okay, and then divided by g. And so therefore my range is going to be equal to this, v squared times sine 2 theta on g. Okay, and we've proven what we want to prove. Right, so I guess we could write QED for this as well. Let's have a look at the second part. Show that if v squared is less than 100g, or 100 times g, then the horizontal range of the ball is less than 100 meters. Okay, so we're given now that we have to suppose v squared is less than 100 times g. Okay, and then we want to prove, and we're required to prove, let's write it down. We're required to prove that the ball, or the range, is going to be less than 100 meters. Okay, this shouldn't be too difficult. We already have a value or an expression for the range. The range is equal to v squared sine 2 theta on g. Let's move this up a little. Now we know that v squared, well, we're supposing that v squared is less than 100g. So this range is going to be less than, subbing in 100g for v squared, times sine 2 theta all over g. I can cancel this g with this g. So this is actually equal to 100 times sine 2 theta. But I actually don't want this sine 2 theta. I want to be just strictly less than 100. So how do I get rid of the sine 2 theta? Well, we do know that there is an inequality relating our sines and cosines, but in this case we're just dealing with sines. We know that sine of any angle is always going to be, or the absolute value is always going to be less than 1. Okay, this is another way of writing sine of x is in between 1 and minus 1. This should actually be less than or equal to. Okay, so we know that it's always going to be less than 1. Doesn't matter what the angle is, whether it's 2 theta or it's some crazy function inside the sine, the value of the sine is always less than 1. So I know that this is less than 100 times 1. I know this, I might put an actual times sign here so we don't mistake it for a decimal point. So it's 100 times 1, which is equal to 100. Okay, and then the reason for that is because, or since sine of x, the absolute value of sine of x is always less than 1. Okay, and so therefore I've actually shown what I want to show. The range is always less than 100. Okay, and that's part 2 done. It is now given that v squared equals 200g and that the horizontal range of the ball is 100 meters or more. Show that theta is between pi on 12 and 5 pi on 12. Okay, so the question says that v squared is equal to 200g, and also we have that the range is 100 meters or more, which means the range is greater than or equal to 100. And we also have from the first part that the equation, or the expression for the range, was v squared times sine 2 theta all divided by g. Now we can substitute v squared equals 200g into this, and we'll get 200g times sine 2 theta divided by g, and we can see that the g's will cancel, and we're just left with 200 times sine theta. Okay, so that's an expression for the range, but we also know that the range is greater than or equal to 100, so we can put that in. This has to be greater than or equal to 100, and dividing by 200 on both sides gives us sine theta is greater than or equal to a half. This should actually be 2 theta. Sine 2 theta is greater than or equal to a half. Okay, so how do we solve this? Well, let's take a slightly easier case and let's have a look at sine of x is greater than or equal to a half. And to solve this, we're just going to sketch sine of x. So really roughly, on the side, do a little sketch like this. Now we know that this oscillates between 1 and minus 1. Now for half, that's roughly about here. So these are the points here that would give us a half. So this point here and that point there. Now obviously the points that are going to give us sine of x greater than a half are the points in between, or the x values in between these two. So this one here is pi on 6. We know that sine pi on 6 is a half. And this one here is 5 pi on 6. It's just 180 minus, or pi minus. Okay, so this blue equation here or this inequality rather, this has solutions of 5 pi, sorry, not 5 pi. Let's make that pi on 6 is less than or equal to x is less than or equal to 5 pi on 6. So what are we solving? We're solving sine of 2 theta is greater than or equal to a half. So that means 2 theta needs to be between pi on 6 and 5 pi on 6, which means that theta is between 5 pi on 12 and pi on 12, okay, as required. So that's the end of part 3. And then part 4, find the greatest height the ball can achieve. Okay, so the maximum height occurs when y dash is equal to 0, or y dot is equal to 0. So let's write that down. Max height at y dot equal to 0. And why is that? Well, that's because the particle has to stop just before it comes back down. And it's obviously coming back down after it's reached its maximum height. So the y direction, in the y direction, our velocity has to be 0. Now, what is our expression for y dash? Well, first let's write what y is. Vt sine theta minus a half gt squared. Differentiating it gives us y dot is v sine theta. Of course, we're differentiating with respect to v, minus gt. And we want y dash equal to 0. So that gives us 0 equals v sine theta minus gt. And so t is going to be equal to v times sine theta on g. Okay? Now this is the time at which the particle reaches its maximum height. But we want to actually work out what the value of that height is. So we have to sub that back into y. So v sine theta on g, when we sub this into y, we get y maximum is equal to v times the time, which is v sine theta on g, times sine theta, minus a half g times v sine theta on g all squared. So we have v squared sine squared theta here, divided by g, my pen's playing up, minus, here we're going to have g on the top and g squared on the bottom. So that's going to give us a total of g, 1g in the bottom. So we have a half, on the bottom there's a g, and on top there's a v squared sine squared theta. So this is going to be equal to a half v squared sine squared theta on g. But what's v squared? V squared is given to us as 200 times g. So this is a half 200 g sine squared theta on g. Let's move this up a little bit. Cancel this g with that g, and a half with 200, leaving 100. So we have 100 sine squared theta. Now this is what the maximum value of y is. However, this is not our final answer because we don't know what sine squared theta is equal to, or we don't know what the maximum value of that is. Not yet anyway. Now, how do I work out what the maximum value is going to be? Well, let's have a look at what the sketch of sine squared looks like. Let's have a really quick look on the side here. So sine squared, if we think about what sine looks like, it's that oscillating one that goes above the x-axis and below the x-axis. Now sine squared, everything that's in the denominator, or the negative values, sorry, not in the denominator, below the x-axis, everything below the x-axis, which is negative, once it gets squared, becomes positive. So it's going to look something like this, and then we'll have a bit of a curve here, and keep oscillating like that, and so on. Okay? But anyway, we don't really care about anything beyond this point, which is not pi on 2, that should be just a pi. We don't care about anything beyond that point. And the reason is because we know the values of theta. We only know that theta can go between pi on 12 and 5 pi on 12. So in fact, we're really only looking at pi on 12 and 5 pi on 12. So values in here. Okay, and that's just before we actually turn. So if I was to mark pi on 2, which is the turning point, it would be there. So what we can see is that sine squared theta is increasing. It's actually monotonic increasing in the domain. Let's write this fully out. In the domain pi on 12 is less than or equal to theta is less than or equal to 5 pi on 12. So what does that mean? It means that if it's increasing, the lowest value is going to be at the endpoint pi on 12, and the highest value it can have is going to be at the endpoint 5 pi on 12. Okay, so the maximum value that sine squared theta can take is going to be sine squared of 5 pi on 12. So we can say, therefore, sine squared theta takes a maximum value at theta equals 5 pi on 12, which means that y maximum is going to be 100 times sine squared of 5 pi on 12 meters, and that is the maximum height that the ball attains.